Hi, and thank you for attending this talk. I'm Nirav, and today I'm very excited to talk to you about our work on caching with delayed hits. This is joint work with my advisor and collaborators at CMU and Microsoft Research. Caches are at the heart of performance critical systems, and here they serve a number of important purposes. For example, caches may be deployed to alleviate bandwidth demand, improve throughput, or to mitigate read delays. Today we'll focus on this third category of caches, which seek to reduce delays. These are latency minimizing caches, and their goal is to reduce the mean latency of all requests served by the cache. Here's a latency minimizing cache that we built at CMU, based on Redis. Its goal is to minimize the average request latency for a cross data center KV store. Now, when a request comes in, traditional caching literature would assume that there are two possible outcomes: cache hits and misses. In a theoretical example, I'm going to show you what textbooks say will happen when I run this cache in a real request sequence. Everything that I'm about to tell you is standard textbook caching, and yet there's a fundamental assumption that we're going to be breaking. So let's see if you can find it. Here we have a client talking to the remote server via our key value cache. Our backing store contains just one object, labeled A. Let's assume that our cache is of size 1, and the RTT between the cache and our backing store is 3 milliseconds. We also have the following request sequence, with a new request arriving at the cache every 1 millisecond. When the first request to A arrives at t equals 0, our cache is empty. Consequently, the cache must first fetch this data from the remote server, and the request experiences a cache miss, with a latency of 3 milliseconds. The next set of requests to A can be served directly from the cache, and experience latencies corresponding to that of a cache hit. In this case, 0. Hopefully all of you found the bug in this example. If not, here it is. We said that it takes 3 milliseconds to resolve a cache miss. So how is it that the requests that arrive just 1 or 2 milliseconds after a miss were served with 0 delay? Clearly something's very wrong. Let's take a look at what actually happens. The first request to A experiences a cache miss, triggering a fetch. Now the RTT to the backing store is 3 milliseconds, implying that the object will only arrive in the cache at t equals 3. At t equals 1, our fetch request is only 2/3 of the way to the backing store. Since the data only arrives in the cache at t equals 3, this request must wait at minimum 2 milliseconds to be served. Similarly, the request for A at t equals 2 suffers a latency of at least 1 millisecond. These requests that are neither cache hits nor cache misses are known as delayed hits. At t equals 3, A finally arrives in the cache, and all queued requests, including the one that just arrived, can be served. It turns out that our caches are impacted by a phenomenon that's becoming increasingly prevalent in today's systems, called delayed hits. The reason that delayed hits are starting to increasingly matter is that the average number of requests that can arrive during a fetch, a parameter that we'll call Z, is starting to go up. Numerically, Z is the ratio between the latency to the backing store and the average inter-request time. It turns out that this is proportional to the product of backing store latency and link bandwidth. Thanks to the efforts of this community, we see a clear trend in these quantities. Latencies continue to go down, and bandwidth continues to go up. However, latencies are quickly approaching their speed of light bounds. For instance, the theoretical lower bound on RTT between Pittsburgh and LA is 34 milliseconds, and we're not too far off from here today. Conversely, link bandwidth continues to grow at unprecedented rates. For example, we're moving to 100 Gbps and beyond in the network setting, and memory technologies such as HBM promise order of magnitude improvements in bandwidth over DDR. So as link bandwidth increases without a corresponding decrease in latency, we expect to see a higher number of requests to arrive during a fetch, increasing the number of delayed hits that we see in practice. First, let's take a look at the impact of delayed hits on our traditional caching models. This graph depicts the behavior of two simulated models in the network setting. One that accounts for delayed hits, labeled actual and shown in orange, and one that does not, labeled idealized. On the y-axis, we have the average request latency, and on the x-axis, we sweep our z parameter. We find that as z increases, the latency estimates derived from hit rate quickly diverge from their actual values. At z equals 10,000, this error exceeds 60%. So we find that delayed hits subvert expectations of traditional caching models and simulators. It also turns out that in the presence of delayed hits, optimizing for latency is a fundamentally different problem than optimizing for hit and miss rates. To properly understand this problem, we start with the offline setting, where we assume an oracle with perfect knowledge of the future. We find the answer to the delayed hits problem in the form of a flow network formulation. Our offline algorithm, belatedly, computes empirically tight bounds on the optimal latency in polynomial time. Unfortunately, I don't have time to explain the flow formulation in detail, but there's two key points about it that are worth noting. First, it's based on a multi-commodity min-cost flow problem, the integer version of which is NP-hard. And second, the formulation introduced us to the notion of aggregate delay, a key component of our online algorithm. I'll come back to this in a few slides. So I said earlier that optimizing for latency is a very different problem than optimizing for hit rate. So what is the difference between the two? First, let's take a look at the hit rate maximization strategy. This is Belody's algorithm, and it provably maximizes hit rate in the absence of delayed hits. Belody uses a simple greedy strategy. If the cache is full, it chooses to evict the object that is used farthest in the future. Unfortunately, Belody does not account for delayed hits, and this leads it to make latency suboptimal decisions. This graph depicts the percent relative latency difference between Belody and belatedly for three application scenarios: 10 Gbps network traffic, CDNs, and storage. We see that for low latency operations, such as DRAM reads or an RDMA access, the gap is quite small. However, as we move towards WAN latencies in the milliseconds, the gap can be quite significant, exceeding 30% in some cases. So we find that for high Z values, the hit rate maximization strategy is actually quite far from true latency optimality. Great. So we know that modeling caches as having only hits and misses, while ignoring the contribution of delayed hits, can be problematic. This is well and good, but what can I do for my key value cache to achieve better latency? The insight, which we learned from belatedly, is that we should incorporate an object's aggregate delay, or its true latency cost. Here's the intuition. When we have a cache miss, it doesn't just affect the latency for that request, but it also affects the latencies of subsequent requests that fall within Z time steps of the miss. That is, the delayed hits. So we must incorporate their cost as well. Aggregate delay is precisely this. It's the cost of the miss, which is exactly Z, plus the cost of delayed hits within Z time steps of the miss. And this depends on the characteristic burstiness of each object. Based on this insight, we designed an offline ranking function. We compute an object's rank as the ratio of its aggregate delay, as defined earlier, to the time until it's accessed again. There's just one final snag. Both the aggregate delay and the time to next access rely on future information, which we don't have access to in the online setting. Fortunately, we can use the past to make predictions of the future. So we use our vast literature of hit rate optimizing algorithms such as LRU, LHD, LRB, and GDValue, to name a few, to estimate the denominator, and we develop a novel, easy to compute estimator for the aggregate delay. Then our caching algorithm is simple. In making an eviction decision, we compute the rank of each cached object and evict the object with the lowest rank. Now that we have our online algorithm, we're ready to evaluate its performance on our key value store implementation. We deployed our caching node in a local server cluster at CMU and set up VMs in 3 different locations around the world: one in LA, one in the Netherlands, and one in Singapore. Using this setup, we measured the average request latency provided by LRU and its MAD variant for each origin location. As the RTT increased from 68 to 223 milliseconds, we saw latency improvements going from 12 to 18%. So, we see increasing gains due to MAD as Z increases. We also tested MAD with multiple backends. That is, the scenario where different objects have different backing store latencies. Despite the fact that this differs significantly from a theoretical formulation, MAD generalized to this scenario as well, yielding a latency improvement of 17% over LRU. We repeated our experiments in simulation, this time testing a variety of application scenarios, Z-values, and baseline algorithms, and we saw similar improvements across the board. Unfortunately, I don't have time to go over these, but if you're interested, we present all of these graphs in the paper. So in conclusion, caches have not just hits and misses, but also delayed hits. As a result, we should design our latency minimizing caches to account for these, especially as we look forward to ever-increasing trends in bandwidth. Thank you, and I'm happy to take any questions.
Um, So I'm waiting for questions from Slack, but let me just get the discussion started. I noticed in your evaluations, you compared LRU and LRU MAD, but did you also compare with the offline optimal or the optimal that you developed?
Sure. Yeah. So we compared our offline algorithm, that is belatedly,
Yeah.
with the offline optimal for the hit rate maximization strategy, that's belity. We unfortunately, and on a comparison between online algorithms such as LRU MAD and the other variants, uh, don't they don't really make sense comparing. It doesn't make sense comparing them against the offline algorithm because fundamentally the offline algorithm has a lot more information than the online one does. So which is why we compared it against online versus online and then offline versus offline.
Okay. A couple of questions have coming in. Jin Jun asked, does every first cache miss lead delayed hits process? Yeah, I think that's but let me go through some of the other questions. So Dave Oran asks, in the simulations, it seems the request rate is independent of the response latency of the cache. What if the clients are adaptive?
That's a good question, and that's something that you might see something with you might see in case of say TCP where your responder is hanging on to or your client is hanging on to the request until it receives a response from the server, and definitely that's something that we need to take into account. So in that sense, the simulations in the network setting don't actually capture that. So we that is something that we would leave to future work to see what happens when you have some kind of dependency between the request rate and the response latency.
Okay, so Balaji Vavanan asks, does belatedly hurt hit rate, and if so, by how much? Roughly, how far apart are they?
That's a great question. Yeah, so like I said, the latency in the presence of delayed hits, latency minimization turns out to be a fundamentally different problem than either hit or miss rate optimization. And when we're looking at the miss rate, that is, the number of requests that you send to the backing store, there is you might actually have to sacrifice the miss rate to achieve better latency. And we performed this evaluation in simulation for all three settings. So this is network, 10 Gbps network, CDNs, and storage. And we found that on average, it hurts the miss rate by the relative degradation in the miss rate is about 1.8% for say network. But this is not always true. For example, in the CDN case, it actually MAD improves the miss rate. So it sends fewer number of requests to the backing store. So it really depends whether or not you sacrifice hit or miss rate depends on the application scenario and the baseline algorithm that you choose to use with MAD.
Okay, so Gianni Antici asks, how do real systems today really handle this? I guess people must be aware of this behavior, but let me also broaden this discussion a little bit. Can you comment a bit on where in the real world you see this being most useful? So it seems like you need to have a high Z and also a high RTT. So can you comment on what are the realistic scenarios where this is most likely going to occur?
Yeah, that's an excellent question. I think so. I'll try to address the second part first, which is where we see this high Z value. And the way we define Z is the ratio of the backing store latency to the inter-request time. So there's really two ways that Z can go up, right? So one is the numerator, that is your backing store latency goes up, which is something which is what we really explored in this paper. So going from a single DRAM access to RDMA to a reverse DNS proxy. That's where your numerator is increasing. The other kind of scenario is when your throughput is going up, in which case your inter-request time starts going down. So these are the kind of two ways that your Z value might go up. So it's not just the backing store latency, but it's also the request throughput. And coming back to the question about where we might where we expect to see the biggest kind of gains of using a delayed hits aware caching algorithm, we believe it's in the context of either CDNs or storage. This is especially relevant in CDNs because the front end or the CDN cache would basically be aggregating requests from multiple clients. And if, for example, if you're watching a popular TV show or you're playing a popular game which has, which caches, say, sprites or something of that sort, you might end up seeing a lot of delayed hits, especially if your origin server is a long distance away. In the network setting, there is kind of a cap on how far your request might actually have to go to get a response. So we see kind of a tapering trend in terms of the gains from using a delayed hits aware cache. But we would really expect this to be relevant in the context of a CDN or a storage server.
That was an interesting talk. While we wait for questions, let me start. These are very interesting theoretical results, and MAT gives good performance. But what are the kind of missing practical features that you've not considered in MAT? Like, how can we, what are more opportunities to make this more practical?
Yeah, that's a good question. So I think one of the starting points would be considering objects with different sizes. So we're making a number of assumptions which are consistent with the vanilla caching problem, which is you have uniform backing store latencies, uniform object sizes, and yeah, those are the really the two biggest ones. So in this case, those are the ones we're considering. But a natural extension to this would be, what happens when you have different object sizes? How do you incorporate this extra dimension into your online or offline caching algorithm? I will say that in the offline setting, considering different object sizes makes the problem strongly NP complete. But it's something that we can definitely do in the online setting. So it might be worth looking at what an online algorithm might look like.
Yeah. So going back to the different sizes. So what if we have a very large object which requires multiple RTTs? How does this change delay hits?
That's a good question. So in our model, we really only considered the scenario where you have essentially kind of like cut through, where you have the object is transmitted as soon as it's received by the cache. But as soon as you consider multiple RTTs or anything involving some kind of queuing, this would exacerbate the effect of delayed hits. So that's something we don't consider in this work. So that's something we would leave to future work. But it's definitely a very practical problem that we expect will have an impact both on the effect of delayed hits as well as on practical systems that choose to or attempt to incorporate delayed hits aware caching algorithm. So that's definitely something we would like to see.
There's a question on Slack. Is there a possibility to utilize ongoing partially downloaded objects in the cache? Oh, that kind of connects to your cut through.
Right.
Yeah.
Yeah, I think that like Sangeeta asked, I think that's basically in this scenario we're really assuming that as soon as you have the first byte, that's being transmitted immediately. So what's dictating this this latency is really the RTT between the cache and the backing store. But yeah, it might be worthwhile looking at what happens when you have these large object sizes, and maybe cut through isn't feasible in that case.
Mm-hmm. And a quick question: in practice, do you know what is the ZValue, or were you mostly working in like a simulation kind of setting?
Yeah, that's a good question. So the way we define Z as the ratio of this backing store latency to the inter-request time. Mm-hmm. The inter-request time would really depend on the workload. So for example, in the CDN setting, for the trace we used, the IRT was 1 microsecond. So this is a relatively high request rate. And depending on where your origin server is located, you might have different Z values. So for example, I'm in Pittsburgh at the moment. So one that's located in Pittsburgh might be like say a millisecond, in which case our Z value may be 1,000. But if it's located in say Singapore, that's 226 millisecond round trip. So in that case, your RZ would be 226,000. So it's really a combination of what the average inter-request time for the workload is expected to be, and what the backing store latency is.
Mm-hmm.
And yeah, I think the point we were getting at was moving forward, we would expect to see higher throughput without a corresponding decrease in latency. In which case, for the same backing store latency, we might see a higher Z value and thus a higher number of delayed hits for the same request sequence.
Mm-hmm. Okay, I think that's all for the questions. Thanks, Nirav. Very interesting work.
Yeah, thank you so much.